Alright, so this is going to be lab 3, the magnetic field of a bar magnet. And firstly, we're going to just do some general introduction. So concepts that students need to be comfortable with are distance dependence and the Biot-Savart law, and that's mainly just to go ahead and do some calculations later on. And then, what is the purpose of this lab? Well, it's to observe and gather data about the magnetic field of a bar magnet or a magnetic dipole, determine the magnitude, the magnetic moment of said dipole, as well as notice how that field strength relates to distance. And then the results I got were the dipole moment of this magnet, I got to be about 1.868 joules per Tesla. And then the constant distance between field strength, I got to be negative 3.24. So what I mean by distance dependence is that we know that magnetic fields of a bar magnet are going to fall off with distance, and that's going to be given by some magnitude of field strength multiplied by a constant k, multiplied by the distance raised to some power. Now, we expect that power to be negative 3, but we need to confirm that, and as previously mentioned, it was slightly off due to some variations. Then we need to be comfortable with the magnetic field magnitude formula, which is basically just the field of a dipole, which is shown to the right. And one thing to note is that the field should point from north to south, and that matters within our next assumptions and actually setting up the experiment. So for our assumptions, we're firstly going to be assuming that the x-axis is along the width of the phone, the y-axis is along the height, and the z-axis is going to point out of the screen. Then we're going to go ahead and have the magnetic field be proportional to some constant times the distance raised to some power. And then we're going to assume everything else is constant except the distance, meaning that if there's any changes in your actual magnet, we're going to just go ahead and ignore them. Alright, so how do you actually do this lab? Well, what you're going to need to do first is determine magnetic north. And how you're going to do that is you're going to lie your phone flat and rotate it until the x component is 0, and you're going to do this by downloading Magnetometer app, my bad. Then, once we determine where magnetic north is, you're going to set up a ruler stick or a meter stick perpendicular to that north. And then the reason why we're doing that is to minimize the field effects from Earth. And then we're going to locate the magnetometer of an actual phone. And how we're going to do that is sliding the phone along the axes in the x and y direction. And then we're going to mark it off using tape. Lastly, we're going to actually collect data, and how we're going to do that is moving the phone to various distances along the meter stick, and then we're going to go ahead and do that on axis and off axis, and then we're going to record that data into a spreadsheet, which will generate a plot for us. Now, I'm going to go ahead and just skip over some of my actual measurements, and I'm just going to jump into the actual plot, because everything is going to be based off of this plot. The first thing is that we need to actually approximate r, and to do that we need to use a logarithmic plot. So we're going to be plotting ln of b versus ln of r, and that's going to convert the formula from the magnitude of the b field is equal to k times r raised to some n, and that's just going to be ln of bx is equal to the natural log of k multiplied by n times the natural log of r. And so as you can see from my values above, those are the b field lines, the natural log of the b field that I got, and the natural log of r that I got. And so what that actually means is this is how it looks. So as you can see, it's approximately linear, which is what we want. And so we also have a point slope form, or a general slope form. So what that means is that, in this case, our n would be negative 3.2394, when we would expect to be negative 3. And what we're going to do with that k value is actually determine our magnetic dipole moment. And how we're going to do that is go ahead and reconvert the k, and that's going to be equal from the Biot-Savart law of mu naught over 4 pi multiplied by 2 mu. And so we're going to go ahead and solve that and rearrange that to solve for mu, and then we're going to be using that value a little later on and actually using the glow script media and actually to calculate that. So now we're going to move on to the off-axis measurement, and how we're going to do that is go ahead and get position our phone a distance of d perp in the x and y directions, and we're going to measure the field with the app. And so my average d perp was 0.17. I got a b field of 1.74 e to the negative 4 Tesla. Now we're going to be using the simulation and glow script to actually compare these values with what would be ideal. And my measured values that I previously got were 1.60 negative 4, 5.3 negative 5, and 3.90 negative 5 by comparison with the computed of 6.72 e to the negative 6, 2.02 e to the negative 5, and 0. So as you can see, there's a massive difference. And this is actually just the code that I use, and so to calculate for the E field, you can see that code, and then everything for the actual distance is determined by the actual D perp, which, like I said, I use my average distance of 0.17. So then moving into the simulation model, we want to go ahead and model the magnetic field for a couple of points, and we're going to color them differently, and that's just the vector formula that I used in order to actually approximate that, and that's actually how my simulation worked out. And as you can see, the mu that we calculated was 1.86817, and then, yeah, my field came out to be all of that good stuff. And then lastly, I want to go ahead and answer some reflection questions. So what if we hadn't oriented the experiment to compensate for magnetic north? Well, all readings would have been skewed towards that magnetic north, and all values would have been less accurate due to this slight skewing, meaning our mu, our n, and our k would all have been off. So that would not be good, so make sure to actually orient this properly. And then secondly, what if we were to run this experiment with two magnets stuck together end to end? Well, the field direction would be the same because it would still point from north to south and north to south, but we would expect the field to nearly double due to the actual strengths of the magnets combining and actually just and the actual magnetic moment doubling. So yeah, that's it overall. I would like to thank you guys for listening in, and have a good day.